Welcome to this explainer. Have you ever looked at a massive, tangled wall of wires, or one of those incredibly detailed circuit diagrams, and just felt your stress levels instantly spike? Trust me, it happens to the absolute best of us. It's completely natural to feel overwhelmed when there's just way too much going on all at once. But today we're going to take a deep breath. We're looking at a concept that is fundamentally about reducing that exact stress. It's an elegant mathematical tool, but honestly, it doubles as a pretty fantastic philosophy for problem solving in general. Okay, let's dive into the superposition theorem.
So, imagine you're trying to listen to three different people talking to you at the exact same time. It's completely overwhelming, right? You literally can't process the information. Well, electrical networks feel the exact same way. How do we measure the response of a system, the currents and voltages, when it's being pushed in multiple directions at once by several different power sources? Our natural instinct is usually to just wrestle with massive, multivariable equations right out of the gate. But what if we didn't have to do that at all?
And that brings us to the principle of superposition. Simply put, the net effect of the sum of causes equals the sum of their individual effects. Now, what's really fascinating here is how it translates standard physics into almost a philosophical logic. In circuits, a cause is just an independent voltage or current source. It's the thing pushing the energy. The effect is the resulting voltage or current flowing through a component. This principle promises us that the big, messy total is exactly equal to the sum of its isolated individual parts.
When you're staring down a setup with a 100-volt source on one side, another source on the right, and multiple loops intersecting everywhere, the math gets really dense really fast. Engineers actually call these multiple sources forcing functions, which, let's be honest, sounds pretty intense. It sounds like the system is being forced into chaos. And faced with that chaos, we try to calculate every single interaction simultaneously. But superposition gives us a special kind of permission. It gives us permission to stop multitasking. We don't have to solve the whole mess all at once.
The entire philosophy basically boils down to a massive sigh of relief, one cause at a time. We calm the chaos by essentially turning off everything in the network except for one single cause. We isolate. By looking at how the circuit behaves under the influence of just one source, we turn a high-level, headache-inducing engineering problem into a basic, foundational analysis. Seriously, it's the ultimate hack for anyone who gets overwhelmed by too many variables.
Okay, so how do we actually pull this off? It's a beautifully straightforward, low-pressure, four-step procedure. Think of it like a simple recipe. Step 1, select a single source acting alone and turn everything else off. Step 2, find the response for that specific simplified setup. Step 3, repeat those first two steps for every single independent source in your circuit. And finally, Step 4, add all those individual responses together. That's the whole shebang. Complex problem solving is really just a series of highly manageable, bite-sized tasks.
Let's look at how this builds in practice. Step 1 has a very specific instruction on how we literally silence the other sources so we can focus. We short the other voltage sources and open the current sources. Think of a short circuit as replacing a battery with a plain flat wire, dropping its pressure to exactly zero. Opening a current source, that's like cutting the wire completely, leaving a physical gap so absolutely zero current can flow. By doing this, we physically remove all the distracting noise of those other inputs.
Seeing this visually really drives it home. Notice how, when we want to focus on just the first voltage source acting alone, the second one is replaced by a short circuit. It becomes a straight line. Poof! It's just gone. And then, when we reverse it to consider the second source acting alone, the first one vanishes into a flat wire. What was once a complicated, tangled, multi-source network is now just two incredibly simple, straightforward circuits.
So the crucial part is what happens after we solve those super simple circuits. Once you find the current or voltage from source 1 acting alone and then source 2 acting alone, you move to the final step, the algebraic sum. You literally just add them together. It really is that easy. If the first source pushes 2 amps to the right and the second source pushes 1 amp to the left, well, the algebraic sum gives you the true final reality of the circuit.
Let's lock this in with one more example. If you isolate a 4-amp current source, the competing voltage source gets short-circuited into a flat wire. Do the reverse, and the voltage source is active, but the current source is open-circuited. The wire is physically broken, removing it from the equation entirely. That daunting, scary circuit is completely disarmed. You just solve for the voltage in scenario 1, solve it in scenario 2, and add them up.
Now, it feels almost like a magic trick, which naturally leads to an important question. Does this work for absolutely everything? Well, the short answer is no. And honestly, that's completely okay. Every good engineering tool has its specific use cases and its boundaries. Knowing when not to use a tool is just as important as knowing how to use it. Plus, knowing these boundaries actually reduces test-taking anxiety because you'll never be caught off guard.
So, let's talk about knowing those boundaries. There are 3 specific ones to keep in mind, and I like to frame these not as failures of the theorem, but as comforting guide rails so you know exactly when you're safe to use this tool. First, the circuit must consist of linear network elements, things like your standard resistors, capacitors, and inductors. Second, because of that rule, it is not applicable to nonlinear devices, like diodes. And third, and this is super important, it is not useful for direct power calculation. Let's expand on that last limitation for a second. Power is nonlinear. Why can't we use superposition to find power? Well, think back to the basic formulas. Power equals voltage times current, or current squared times resistance. Because power relates to the square of the current or the voltage, it has a nonlinear relationship. Superposition relies purely on clean, simple, linear addition. You can't just add squared values together and magically get the right total. So, pro tip. If you ever need to find power, just use superposition to find the total current or voltage first, and then calculate your power.
When you strip away all the dense mathematical language, the heart of this theorem is incredibly peaceful. Just think of it this way. Complex networks are really just simple circuits waiting to be isolated. Whenever you feel overwhelmed by the sheer number of variables in a problem, whether it's an intimidating diagram for your midterm or a massive project in your everyday life, remember that huge problems are usually merely small problems stacked together.
And that is what you should take away from this explainer today. Tackle complexity one source at a time. You have the tools to break things down. Silence the noise, short the other voltages, open the other currents. But before you go, it kind of leaves you wondering, if the principle of superposition works so perfectly for untangling physical circuits, what other incredibly complex systems in our daily lives could be solved just by turning off the extra noise? Thanks for joining me to explore this brilliant principle.